Get into.
We are on the record now.
Very good. And anybody who needs to leave because they have a guilty conscience can do so. Right. Okay, so today we welcome Robin Selinger, who is a professor of chemical physics at Kent State University in the Liquid Crystal Institute. She completed both undergraduate and graduate studies at Harvard University, and then did postdoctoral work at UCLA, University of Maryland, and NIST. She joined the physics faculty at the Catholic University of America in 1995 and spent a sabbatical at the Naval Research Laboratory, 2002 to 2003. Then she moved to Kent State University as a full professor in 2005. And she's a very distinguished physicist. She was named a fellow of the APS in 2016 and elected an APS counselor in 2019, and then to the board of directors of the APS. So if it's anything you need to complain about for the APS, Robin's the person to go to. And we're looking forward to her talk, which is on modeling mechanical actuation in liquid crystal polymers. Robin.
Thank you, Phil. So one thing to let you know, the Liquid Crystal Institute has changed its name. It is now called the Advanced Materials and Liquid Crystal Institute to reflect a somewhat broader research agenda. And the other issue is that our graduate program that used to be called Chemical Physics has been renamed Material Science, which is to say the administrative people at Kent State want us to be less particular, focused on liquid crystals and broader, but we remain pretty much focused on liquid crystals and materials that are liquid crystalline. We are always looking for recruits for the graduate program. So if you have any students majoring not only in physics and chemistry, but thinking more broadly, materials and especially chemical engineering, Jay, those students are very well suited for our graduate program, having a strong fundamental background in both physics and chemistry and advanced mathematics. And we really love to welcome those students. So anyway, the story I'm going to tell you about today is very, very transdisciplinary. It reminds me of the fable about the blind people and the elephant. That some people think the elephant is very like a tree or like a garden hose. It has so many different aspects. Liquid crystal polymers have physics, chemistry, mechanical engineering, device engineering, all kinds of features about them. And I'll try to give you some flavor about how all these different disciplines have been contributing to the development of liquid crystal polymers as soft actuators, programmable materials. So first things first, I know not everybody here is a soft matter person, so I thought I'd remind you that liquid crystal phases are mesophases of non-spherical molecules, and they typically have, any given material may have any given set of phases, but the simplest one is that if you have an isotropic liquid made out of, say, rod-shaped particles, if you cool them down, they may form an aligned nematic phase. And you have some liquid crystal gurus of your own in the Case Western campus. So I imagine there's quite a few experts here who know a lot more about this, maybe even than I do. But so after the nematic phase, there may be layered phases, the smectic phase. Smectic A is untilted, smectic C is tilted. There's a whole panoply of other smectic phases. And then if you make the system cold enough, eventually it will crystallize. The materials I'm going to be telling you about today are in the nematic phase. And what's the most interesting piece of physics about this is that the degree of orientational order in a nematic is defined by a scalar order parameter that tells us how well aligned the molecules are. And if you heat them through the phase transition, they go from essentially fully ordered to fully disordered. But in between, the quality of the order changes. And so the scalar order parameter is actually a function of temperature. And that is the key handle we have to make liquid crystal polymers actuate. So just to show you some experiments, here are some little videos. So let's see, way over here on the left side, can you guys see my little arrow spinning around here? There is a very thin piece of liquid crystal polymer here. This is an experiment from our colleagues at the Naval Research Lab. And this coil, they're just running current through it to warm up and cool down this little piece of elastomer. And so when the material is hot, it's short, and when it's cold, it's long. And when I first saw that, I thought that was kind of curious. You know, my mom taught me when I was a little girl that things expand when they heat up. And it's like, you know what? This one shrinks when it heats up. It actually expands in the other two directions. So the volume of the sample is more or less conserved. But yeah, it changes shape with temperature. And so when you look at this, you'd say, wait, that's artificial muscle. We could use that in a robot. This other video on the right side, this is also an experiment from the Naval Research Lab. This is a very thin piece of a polymer film that's been coated front and back by a conforming electrode. It is conducting grease, and then they're applying a voltage from the front to the back of the cell, just like you would do for a liquid crystal display. And what's interesting is it doesn't change color, it flexes. And so a positive voltage makes it flex one way, a negative voltage makes it flex the other way. So that's kind of interesting. It's a different effect than heating. And then here's one that's photoexcitation. I'm sorry, this one isn't a movie, it's just still a still image. So you have a picture here of a cantilever beam, a couple millimeters long. This is work by Peter Palfi-Mahori, my colleague at Kent State. And then you shine a laser pulse on it, it will actually bend in response to light. So we can have actuation by temperature, actuation by light, or actuation by field. I should also mention my colleague, Tony Yockley, is actually working on ionic liquid crystal elastomers that also flex in response to field. So this is a fast moving research area. So just for these particular examples, what's going on? In the case of the nematic, when you raise the temperature, it might go full isotropic, or it might just have reduced nematic order, and this causes it to shrink. So this is supposed to be a cartoon representation of the polymer. So we have here a polymer backbone, and here the little mesogens that are rod-shaped liquid crystal type molecules are dangling off the main chain. They could also be in the main chain. They could be tethered side on or edge on. All those details of polymer physics are interesting and change the material properties. But the key issue is that when the molecules undergo a change in their orientational order, that the material actuates. And it typically actuates by shrinking along the axis of nematic order and growing a little bit in the other two directions. Okay, in the case of the light actuation, that polymer is doped with an azo dye, some kind of azobenzene derivative that undergoes photoisomerization, or photoexcitation. So when you have the material in the relaxed state, let's see, which one is that? The trans state, when it absorbs a photon of just the right wavelength, it will undergo a conformational change to a cis or bent state, which disrupts nematic order. And then the material that's been exposed to light will also locally shrink. And in this case, the top of the little cantilever, where the part of the sample that was impacted by the light has locally shrunk, and the back didn't get the light, so it bent because the front shrinked and the back didn't. In this case, the direction of nematic order is parallel to the long axis of the beam, so it bent up, kind of like, let's see, the bimetallic strip that we all study that is used as a thermometer. If you just have, some reason why it would bend from a change of temperature. In the case of the smectic phase, as I mentioned, is a layered phase, and it's a chiral material. When you impose an electric field transverse to layers, it makes the layers tilt. And like the books on a bookshelf at the library, if they all tilt over, you get a change in the layer spacing, and this causes a mechanical contraction. You would think the whole sample as a result would just shrink and maybe shear a little bit. Because it's not completely flat and because there's a little asymmetry between the front and back of the sample, it does also make it twist. Okay, now in those cases, the nematic director was uniform, but the nematic director can also be patterned on purpose. And when you do that, the axis of mechanical actuation is not uniform in the sample, and you get some sort of complex shape change. So one of the first things that was done was to put the director field in kind of a target shape. So in this case, the nematic director is pointing around the circle. If you look with cross polarizers, you will see a +1 defect, which means there's a 300. That's the point with the 4 black stripes. That means that where you see black, the nematic director is parallel to either the polarizer or the analyzer. And those 4 stripes mean there's a 360-degree rotation inside. And then when you heat it, you get something that looks like a volcano. Or for the group from the Netherlands, this is Lawrence de Haan, who was at that time a graduate student in the group of Dick Brouwer. He decided to put his little disc, instead of putting it on a table or floating it on a little bit of water, he sucked it onto a little glass tubule. And then when he shines light on it from the top, you know, a heat gun basically to warm it up, it forms into the shape of a flower. And since they grow a lot of flowers in the Netherlands, I thought that was particularly lovely. Another type of non-uniform nematic director that can be used in the system is to, let's see if I can move this command thing a little bit so I can see my own slides, is to put a twist in the material. And this is a common thing to do in the liquid crystal community, because the very most common liquid crystal display that you would find in, you know, a cheap alarm clock, or actually my cell phone has one. This is my house phone, has a little liquid crystal display on it. They're twisted nematic displays, and they have a 90-degree twist of the nematic director from one side of the display to the other that's imposed through surface anchoring forces. Well, the same kind of thing can be done here, and we can have a liquid crystal film that has a twist of the nematic director from one side, you know, across the very thinnest axis of the film. And then when you heat it, it can form into some kind of helix. And now we are inspired by Italian pasta. You know, what kind of pasta looks like this? What kind of pasta looks like this? So this is more like rotini. This is, you know, more of a hollow tube. And then the last thing we can do is we can put splay. So we can treat the surfaces that are used to form this liquid crystal, where on one surface, the liquid crystal wants to lie parallel to the surface in a kind of planar anchoring. On the other surface, it wants to lie perpendicular, what we call homeotropic anchoring. And that splay, when you heat it, the bottom side wants to shrink, and the top side is shrinking vertically, and that also gives rise to a bend. So these are a different sort of, if you think of them as sort of pattern elements that you could combine to make an arbitrary shape transformation in one of these materials. So they truly are programmable solids. So let's see, why am I not going to the next page? There we go. So the first way that these materials were patterned was to take two pieces of glass. This is, again, just exactly something like you would do with the liquid crystal display, and put a surface patterning on them that causes any liquid crystal in contact with the glass to align with a certain orientation. And let's see, Tim White, who is at that time at the Air Force Lab in Dayton, had the idea that he could use, you know, a photopolymerizable coating where he could essentially shine a very thin collimated beam with linearly polarized light, and thereby set an anchoring direction, whichever way the polarized light, and that would be the anchoring direction for the material. And he did something clever. He put two pieces of glass with the coatings on the inside, so essentially an empty liquid crystal cell, and pattern the front and the back at the same time. The advantage of that is if you pattern two separate ones, then you have to try to align them. But if you sort of attach them together and pattern them at the same time, because the polarized light can penetrate through the first glass into the second one. Then in particular, you can write a bullseye pattern like this one, or you can write any pattern. In fact, to celebrate Peter Palfy-Mohori's birthday, they took a picture of him and they converted the grayscale picture into an angle and wrote it so they could essentially make a picture of Peter on the liquid crystal elastomer. And so in this case, once you've patterned the front and back substrates, then you fill it with a liquid, which includes liquid crystal monomers, the polymer material, the monomers that are going to make the polymer, the cross-linking agent. And then you shine, you know, you put that stuff inside the patterned substrates and let the liquid crystal relax itself to align with the pattern on the surface. Then shine UV light through the glass to polymerize it. And then if you take it out of the glass, and hopefully that will work, then you get a piece of polymer that has that same liquid crystal orientation field, what we call the director field, uniform through the thickness. Of course, that depends on the cell not being too thick. And then when you heat it, it will transform into whatever shape. And considering that it has the bullseye pattern, it would make a cone. And so you get essentially a two-dimensional object. You can also put some twist in it, so that you can put, instead of patterning the two pieces of glass at the same time, you can pattern one piece of glass with the pattern and the one behind it with, say, a 90-degree twist. And if you dope the liquid crystal with just a little bit of chiral dopant, which breaks the symmetry between rotating clockwise or counterclockwise between the two substrates, you can actually get some of those twisted structures. But whatever this is, it's essentially a very thin two-dimensional object that's flat and it's as polymerized. And then when you heat it, it could transform into any kind of 3D shape. So that was the very first method that was used for patterning these things. The second method I mean, you could also impose the anchoring surfaces other ways. The old-fashioned way to do it, again, from the early generation of liquid crystal displays, is simply to rub the surfaces. And that was also used as a technique for, besides photo patterning. And actually, my colleague, my former colleague now, Chi-Ho Wei, who has moved back to China, also invented some patterning techniques using metamasks, and again, using polarized light to pattern, and you can put like all kinds of complex patterns on. So a newer method is to use 3D printing, except to be kind of trendy and cool, they call it 4D printing, because after you've printed it, it's going to change shape. So time is your fourth dimension. So the very first person who published, there was a race, a lot of people were working on it. Taylor Ware, an upstart assistant professor at the University of Texas at Dallas, who I believe has since moved to Texas A&M. He was the first one who published in 2017. Dick Brower, one of the senior leaders in this field, quickly followed. And Tim White, working with now at the University of Colorado Boulder, and Jennifer Lewis at Harvard, followed soon after. So the idea here is simple. Instead of having some sort of pattern substrate, what we'll do is we'll just have a 3D printer that is spewing out the material, and it will polymerize quickly after being extruded. But in this case, the alignment of whatever the special direction, the nematic director, comes from the extrusion direction. And so then the material is going to shape transform from whatever you built into something else. And this is an example from Taylor Ware's first paper, where they used the 3D printer and they were printing in kind of a spiral pattern, and they built something in the shape of a hat with a brim. And then on transforming, it popped through and made something that looks more conical standing up. So this brim popped down, and this shape transformation was programmed by the way they extruded it. There's yet a newer way. This was published in 2019. Ravi Shankar, working together with Taylor Ware. Ravi is at University of Pittsburgh. And so what they did was a layer by layer deposition of a very thin film of again, a non-polymerized liquid crystal elastomer. And then they used a magnet to orient the director in the unpolymerized material. And then they selectively polymerize different places. So they can make objects of different shape, and they'll have essentially a 3D control of the director in each voxel. So there are going to be more and more interesting ways to pattern these materials. But each of these patterns, again, represents a program, not just for an initial shape and a final shape, but a complete choreography of motion when the material is stimulated. And as I showed at the beginning, you can stimulate the shape change by a change of temperature. If the material is doped with the azo dye, it can be actuated by shining light on it, or it can be done with an electric or magnetic field, depending on what the material is sensitive to. And one of the cool things about that is that, even the stimulus doesn't have to be uniform. You can shine light selectively on the sample, or shine light on one side and not the other side. And so all kinds of programmed motion are possible. So here is another experimental one. This is from Natalie Katsonis, who was at University of Twente. She has moved to another university in the Netherlands. So this is, again, driven by trans-cis isomerization. And you can use one wavelength to make it change shape one way, and actually a different wavelength of light will make it change the other way. So there's a large community of researchers studying liquid crystal elastomers. There is an international conference taking place once every 2 years. The last one was in Eindhoven in the Netherlands, hosted by Dick Brower's group. That was a little over a year ago in fall 2019. And the next one is supposed to be coming up next year. We'll see if we get that far. Let's hope. And let's see, there's more people. Chris Bowman has been working on making materials where you vary the degree of polymerization and get different kinds of response. There's all different ways of patterning these materials. So the question is, if I, as a scientist, want to predict, I know a material shape, the initial shape, and I know the director field that was fabricated through one of those methods, how do I actually model it? And when I started looking at that, I was thinking, well, holy cow, I've been doing molecular simulations and Monte Carlo simulations my whole life, but this is modeling, this is like engineering. I need to know the shape of this thing, and I need to describe it on timescales of seconds, if not minutes or hours, and I need length scales of centimeters, if not, these are macroscopic objects. So I decided to essentially give myself a crash course in mechanical engineering. and write myself a finite element code. Now, a lot of people know about finite element. It's used to integrate differential equations forward in time in many different contexts, not just elastic deformation of materials. And many people will purchase a finite element code. I mean, COMSOL is sending me advertisements at the rate of 2 or 3 a day sometimes. And there are a lot of other finite element codes that are available, for sale or for free. But I'm a physicist. I'm a computational physicist. I'm independent. I like to write my own code. I don't want to use a commercial code. And I didn't think there would be a commercial code out there that would have the physics and chemistry of liquid crystals and their actuation by field. I mean, it's a real, genuine multi-physics problem, and probably COMSOL could do it, but I wanted to write my own code. So here's what I did. I said, let me write a Hamiltonian. I am a physicist. I will use a Hamiltonian. And what does a Hamiltonian have? It has potential energy and kinetic energy. How easy is that? So the first thing is I need to be able to describe a potential energy of a piece of elastic that's been deformed. And the simplest thing to do is to think about Hooke's law. That's 1/2 kx squared. I guess we teach that to our freshmen learning about mechanics. But this is for a continuous elastic body. So what I really want to do is write the energy as a function of strain. Okay, and that meant I had to go learn some solid mechanics. So the tensor equivalent to 1/2 kx squared is to have an energy that depends on the strain tensor with a quadratic form. But it's a tensor, so you have to have a sum ijkl. And then thecijkl is essentially, it's like the Hooke's law constant. It's a stiffness matrix, but it governs, it has in it, the bulk modulus and the shear modulus. And depending on the symmetry of the material, we can have, only a very small number of those terms in CIJKL will be different from 0. This V here is just the volume. So this is an energy density that goes like strain squared. And the other issue is if you use the linear version of the strain that just has one derivative of the displacements with respect to position, this energy is not invariant under rotation. So I had to read Landau and Lifshitz and figure out how to use something called the Green-Lagrange strain, which is actually a nonlinear strain. Anyway, that means this is a good potential energy. This is only one potential energy. There's lots of other ways to write the potential energy of a strained piece of elastic, but this is one. Then we have to have a potential energy, and the simple thing is to say, okay, I'm going to divide my sample into a mesh, and I'm surprised I don't have a picture of a mesh here. I guess I'll be showing you a picture of a mesh in a minute. So in the mesh, I'm going to imagine that all the mass in my sample is going to be represented by a set of little mass points that exist at the nodes of the mesh. And so if I put all the mass in those little points, that's called the lumped mass approximation, then it's easy to just write, I mean, any freshman knows that kinetic energy is a 1/2 mv squared, right? So I'll just say all the mass is in the nodes and I have a potential energy. Now I need 2 more terms in my energy. So one of them is a coupling between strain and nematic order. So epsilon ij is a mechanical strain. And then this S is something about the nematic order parameter, and it gets bigger or smaller depending on whether the material is hot or cold. And so when it's hot, the scalar order parameter drops, and when it's cold, the scalar order parameter is larger. That can be a local variable because, for instance, the material might not be uniform in temperature, or it might change with light exposure. And then this is just the QIJ matrix. I say only for my liquid crystal friends. This is tells the system which way the nematic order is pointing. And so the idea is that the scalar order parameter will drop with temperature, and as we're on this curve, even if we don't go through the phase transition, the material will flex when it changes temperature. So now we need a mesh. So if we're going to define, if we did this in 2 dimensions, we could use triangles. But since we have 3-dimensional objects and they twist in 3D, we need to do full 3D. So we will start with tetrahedral elements. It's the simplest finite element formulation. So the finite element code has an energy and everything defined. I mean, so strain has to be calculated for deformation with respect to a reference state. So our model is written such that we have for each element the reference state, that is to say the state at which the material is fully relaxed elastically and has no internal strains. That would typically be when the material is polymerized. That's its shape. And then when it's been heated or stretched or sheared or translated or rotated, those 4 corners of this tetrahedron have all moved to new locations. And then the strain is calculated by linearly interpolating the displacement field from one state to the other. And that means that we're assuming, again, this is a pretty naive, fundamental, basic formulation for the finite element. We're just treating the strain as if it's piecewise constant inside each element. So we don't have to worry about gradients of the strain. But of course, it'll be different in each element. So we can have gradients of the strain across the sample, but the strain is treated as piecewise constant within each little volume element. Okay, so the first thing we did is forget about the fact that it's a liquid crystal elastomer. Let's just see if we can do plain old elastic. So the only terms are the strain energy from strain, the first term in our equation, and then the mass, the potential energy, the kinetic energy that comes from the fact that the nodes are moving. And this little simulation is the one the student, Andrew Coney, he called it dancing tofu. And here color is just indicating the local strain energy. And so here you can see the mesh that is showing us where the tetrahedra were drawn to represent this little slab of material. So if you were eating Jell-O on the space shuttle and you wanted to play with your food, it might look like this. And here's just a disk. So in the case of the disk, it looks like we've succeeded in maybe just exciting one normal mode and it's oscillating without loss. We haven't turned on any dissipation. So, and so in this case, we would expect that the sum of kinetic and potential energy, the sum of all the linear momentum and the sum of all the angular momentum, if there are no constraints, would all be conserved, just like they would be in a molecular dynamics simulation. But now we're moving nodes in a finite element mesh rather than moving atoms. The other thing is, just like molecular dynamics, this is F equals ma dynamics for a set of point masses. So we've replaced the interactions of atoms in a molecular dynamics simulations with the energy. I mean, we could have hooked them together with springs, right? Then it would just be a set of masses and springs. We could do F equals ma. Here, what we've done is we've essentially used this very simple finite element model of elasticity to create forces. And now the forces, it looks like a many body potential, but the forces are a function of the XYZ positions of the nodes in their current state and the XYZ positions of nodes in their reference state. And the forces and energies are calculated element by element, looking at those particles in sets of 4. And it is, just like molecular dynamics, trivial to parallelize, and because you can do the whole calculation for each element in the system at the same time. And so if our students figured out how to implement it in CUDA and run it on GPU-enabled nodes at the Ohio Supercomputer Center. And so these codes run in almost real time. Like the time it takes a piece of Jell-O to wiggle, you can calculate how long it takes a piece of Jell-O to wiggle. And we looked at, so here's another piece of Jell-O you could play with on the space shuttle. So this code was running at 700 frames per second. If we don't add any dissipation forces, then let's see, so what's going on here? This red line is kinetic energy versus time. The blue line is potential energy versus time for this simulation. And this black line is not an axis. That's the sum of kinetic and potential energy. And it is rock solid. So if we make the time step small enough, just like in molecular dynamics, we can have good energy conserving dynamics. Now, the reality is that, you know, if you bounce a rubber ball on the floor, it doesn't come quite back to your hand. There is lossiness in the internal elasticity of rubber. And so we have to add friction and dissipation to the model, or else it would never relax to mechanical equilibrium. And whether it's underdamped or overdamped, that's just a function of material properties. But if we want to turn off all the dissipation, we can really recover fully conservative dynamics. And the few tests I've done with commercial finite element codes, even the expensive ones, they say, oh, you can't turn the dissipation off because then the code is mathematically unstable. And it's like, you know what, ours is stable. So it's a very simple model. It's just the dynamics of elasticity. Okay, so here is an example of how it performs. Let's see, I need to move this thing again. So if we put it on a large mesh that has 1 million tetrahedral elements, run it on a single GPU-equipped node at the Ohio Supercomputer Center with 28 cores, then we can get about 1,000 steps per minute. And this is from the Owens cluster. And, you know, we're using different computer hardware now. There's all different ways of doing this, but it's just trivially parallelizable and it runs fast. I should also say about the mesh itself, it can be structured like this one where you see an underlying cubic lattice, or it can be unstructured. And there are many meshing algorithms that can take a volume of interest and represent it as a series of connected tetrahedral elements, which is helpful. We didn't have to, I am a do-it-yourselfer, as you can tell, but I didn't do that part myself. In 2 dimensions, it's easy to just use a Delaunay triangulation function in MATLAB to take a set of points and draw them into triangles. In 3 dimensions, if you've just bounded the surfaces, it can be a little bit more challenging. But another key issue is, since we're treating strain as piecewise constant, it's important that we have enough elements across the sample so that you could actually, like, if you bend this material, it's going to be compressed on one side and stretched on the other side. If you just had 2 elements, that wouldn't be a very good representation of a linear gradient and strain across a thin film. That's challenging for us, though, because if we want to model a sample that has a really big aspect ratio, our elements have to be pretty tiny because we're meshing across the boundaries. And there are more sophisticated ways to do that, but we're still sticking with the simple ways of doing it. So let's do the simplest thing. If we put that +1 defect, +1 just means the director, the nematic orientation rotates by 1 complete circle. Then we do get, hang on, this movie didn't play right. Let's try that again. So it starts flat, and then when you heat it, it forms first into a hat shape, right? It has a brim. And then as it heats up, it pops through and eventually becomes a cone. And analytical calculations that neglect the fact that there's a thickness that has a bending energy will miss that. They'll go straight from the disk to the cone. So the finite element tells us something that simple analytical approaches will miss. And this pop through also gives rise to hysteresis in the transitions. And then the question is, well, you have a knob, you want to play with it. So topological defects in liquid crystals are quite fascinating objects. You can have more than 1 rotation. In fact, here we have -4 rotation. So if I pointed my pencil along this and turned the pencil, let's see, clockwise as I go around, this is a -4 defect. And when we tried modeling that, when we heat it up, you get essentially a very disordered looking structure. Each of these little sections can pop up or down. There's nothing about this structure that's asymmetric between the front and the back. So part of it will pop up, part of it will back, and it will be disordered. So then we tried another numerical experiment. If we heat it from one side, which is typically what's done in the experiment, they shine a heat gun on the object, then it always pops in the same direction. That breaks symmetry. And we got this very fascinating shape that looks like it could be used to make orange juice or maybe to serve deviled eggs. That's the place where I've seen this kind of shape before. And so you can see it has all these little local features. And so this is essentially programmed shape transformation. Tim White did make some of these high order defects films, but he floated them on water and then tried to heat them, and they were very disordered looking. It's hard to tell what they really look like, but it can be done. And then there's the question about, okay, origami is the Japanese art of folding paper into complicated shapes. Could we program origami? And getting things to fold is really hard. So this is my now former student, Diane Jimenez Pinto. She is a faculty member at Lincoln University in Missouri. And so she was interested in an experiment that she saw, I believe it was from the Dick Brower group, where they took a sample that had a radial anchoring structure on one surface and azimuthal, that is to say, still a +1 defect, but with the director going around in a circle. And putting those 2 things on top of each other, and they tended to make a fold. So she tried modeling what happens if you take a plus sign with this shape, a plus sign with that shape, and you can see it folds. And not only does it fold, but it folds with a beautiful curved fold, which is challenging to do in real life, like with paper, but she can program a fold, which is kind of cool. And this is called the radamuthal box. So radial and azimuthal makes radamuthal. That term was actually invented by Lawrence DeHaan, who had a beer and went back to the lab and decided to try. So what happens when you add one on top of the other? Okay, now the 4-dimensional printing is, now you're starting to make something that could really be a device. So again, this is from Ravi Shankar and Taylor Ware. So I showed you before the thing that looks like a hat and they pop it in. So my student Yusuf Golestani decided to model that. And what's interesting, he's able to take the STL file that controls the 3D printer and use it directly to create the finite element mesh. And he was able to model that transformation. And it also involves a pop through. I think this thing actually can pop off the table when it transforms, kind of like those little polymer toys my kids played with when they were young. So you can see it pops through. Okay, so one of the biggest challenges we had in trying to do these models is to help experimenters figure out what their experiments mean. I mean, that's the whole point of having a model like this. It would be for, to design an experiment or to understand an experiment that was already done. So here is an experiment that was done in Eindhoven by Helene Gellebar, who was at that time a PhD student of Dick Brower. So she has a little thin film here, and she's taken two pieces of it. One of them she mounted right side up and the other one right side down in a kind of a bow shape. And then she shines UV light on it from the left side at an oblique angle, and they move in a really weird way. So in this case, they have wave motion going right to left. And in this case, they have something that looks more like wave motion going left to right. And that one's fast and the other one is slow. Okay, so Dick Brower contacts me and he says, we have this experiment that we really don't understand. Could you help us model it? Okay, so we need to know something about, well, how did they fabricate these films? What's the director? Okay, so they said, okay, one side is planar, so the nematic director is parallel to the long axis of the film on one side. It's homeotropic, or is to say perpendicular on the bottom, and in between it has a gentle splay. This is Anne-Helene Gellebar, and this is Dick Brower, her advisor. And this material is actuated by light. So there is doped into the polymer, this azobenzene derivative that undergoes a trans-cis isomerization when exposed to UV light, and it has a slow thermal relaxation. When the light is removed, it will go back. The chemistry of the azo dye has been adjusted here so that both transitions are relatively fast. They both take a little bit less than 1 second. So when you shine the light on it, in 1 second, it's reached mechanical equilibrium, take the light away, and it will in 1 second relax back to where it was. Okay. And what they were finding was when they put the planar side, that is the side where the molecules are lying parallel to the surface on the top, that was the case where the waves move left to right and fast. Okay. And then when they put the planar side on the bottom and put the homeotropic or perpendicular side on the top, that's when the waves move slow and they move toward the light source. So that was the puzzle. Like, what could possibly make that happen? Okay, and there were some clues. One clue is if you shine the light from the top, nothing happens. Like the material flexes and stops. So, and if it has something to do with shadowing. And wait, there's no light in my model. How do I add shadowing to my model? When the light is shining from the left side, this part is in the light, this part is in the shadow. So actually in the experiment, I think they can either make the sample on an angle or they can put the light on an angle, but they can control that angle. Okay, so the oscillation only occurs if there's a splay geometry in the sample. They tried uniform planar, they tried uniform homeotropic, no oscillation. They only see oscillation if they have an oblique light angle, 10 degrees to the horizontal. So shadowing is clearly involved. And the dynamics matter, and the motion is not underdamped. So the changes in S, that's the scalar order parameter, how nematic the system is, are not uniform in the sample. They depend locally on the light exposure, vary with time. So this is a hard multiphysics problem because the material self-shadows. So I had to figure out, if I have my sample in whatever shape and I shine light, what part is in the light and what part is in the dark. So I went to Starbucks with my friend, the mathematician, and he said, rotate the body so it's in, so it's aligned with the light and it's easy to calculate. So we figured out how to do it. So we use this ray tracing algorithm to figure out which surface volume elements are illuminated. And we said, okay, we know there's this complicated photochemistry, but let's just boil it down to something super simple. We said, let's imagine that the scalar order parameter drops linearly in time when the material is illuminated. And it goes from some highest value to some lowest value in about 1 second. And if you take the light away, S relaxes back to where it was again in about 1 second. So it's a really simplified photochemistry model. And we're like, okay, we'll just let the scalar order parameter have a highest value and a lowest value, the most ordered it can be and the least ordered it can be for that much light. And of course, that would depend on the light intensity and it would depend on the temperature, but just like this big, simple model, like it to be able to run in a finite amount of time. And it actually ran pretty fast. So here's Michael Varga, who actually, I gave the Zoom link to this call, so he might be with us if you want to ask him any questions, because he's local to the Cleveland area and still in grad school, actually. So this was his model. the first one he did that showed that oscillation. So this is the light is on the side toward us. Where you see red, that's the material that has light exposure and is moving. So we set the system up first in a shape and let it come to equilibrium, and then we start shining light. And you can see the waves are moving away from the light source. Okay, so the light is not penetrating through to the bottom very far. So let's look at the actual, compare the simulation and the experiment. So on the left is the simulated model. On the right is the experiment. This is not exactly the same simulation. And you can see they have a bump that doesn't go away. The previous simulation also had a bump that didn't go away. This one, the bump does manage to annihilate, but you can see the wave motion is driven, light exposure on the left side. And the waves are moving away from the light source just from the point of view of what we were modeling in the simulation. Like I said, this is not a molecular simulation. This is at the lab scale. We modeled something, 40 seconds of motion, and the model, it ran in 25 minutes on a single CPU that had GPU acceleration, had multiple cores, and we had this was a simple simulation, a tetrahedral mesh with less than 6,000 nodes and just under 20,000 volume elements that are tetrahedral in shape. If we do the same thing with the homeotropic side up, the waves move the other direction, which is to say toward the light and much more slowly. And now the light is coming from the left side. And you can see that there's definitely a pop through behavior, which is driving the wave motion. So slower and in the opposite direction. Okay, so we had very simple assumptions in this model. It more or less reproduces the behavior in the experiment, not exactly, but pretty close. So then the people who did the experiment, Angel and Jelibar, came up with a brilliant idea. Instead of having the sample tethered on a little, on the table, how about putting it on a little frame and putting it and shining the light and see if it will move? And they succeeded in making a light-driven robot. So this is a little piece of ribbon, has no battery attached. It's just being powered by light being shown on it from afar, and it crawls. Here it's on a mirrored surface, so you can see, and they're trying to have it, go over a barrier here. And let's look at the other one. If you flip it over, it's the same device, just flipped over and shine light on it. It moves toward the light, but much more slowly. So they were able to harness this motion, this light-driven motion, to create essentially an autonomous light-driven mini robot. I think robot is kind of an extreme word for it, but it does move, and it moves away from the light. If it's in one orientation, it moves toward the light if it's in the other orientation. Okay, so what else can we do? Anyway, if you want to read about this work, we published it in Nature in 2017. Last year, I created a tiny.cc link that will take you to, I think, my Google Scholar page, or maybe I think it's my campus homepage that will give you a link to some recent papers. And it has, more details about these mechanisms. What we've been doing more recently is we've been collaborating with Oleg Larventovich's group. Greta Babahanova was one of his graduate students. She's currently a postdoc at NIST, and she's been looking at liquid crystal elastomer coatings. So just to give you a quick orientation, one thing she did is she put a network, not just a single topological defect, but a bunch of defects in a liquid crystal film formed between two pieces of patterned glass. But instead of taking both pieces of glass away, she only takes off one piece of glass, leaving the liquid crystal elastomer as a coating on the other piece of glass. So this material is not going to deform into, a bust of President Lincoln. It's just going to have small deformations off the glass because it's attached hard to the glass below. So it has very small displacements, but they are interesting. So for instance, this material, when you heat it, depending on how, depending on how it's built, it can either have dimples or little spikes. Excuse me. So it's a programmable coating now. And here's an example of how the finite element model compares to the experiment. And you can see the little dimples growing. So now we can start engineering coatings that are responsive to whatever kind of stimulus. It could be temperature, could be light, various things. And we can have dimples, we can have spikes. So again, this is experiments, this is the simulation, this is what the actual microstructure of the thin film looks like. And in this case, The director orientation is uniform through the thickness, and these coatings that have this interesting pattern we're fabricating using the technique, the MetaMask technique developed by Chi-Ho Wei, then at Kent State. Now he's in Shenzhen. So I think I will skip some of these details. We were able to use analytical calculations to figure out exactly how those things look as a function of the angles involved and higher order defects. Now I want to talk about octopus. Octopus are some of the coolest animals in the animal kingdom. And one of their superhero capabilities is they have these amazing suckers that exist on their 8 arms, which they can use to pick things up using suction. And, you know, underwater, they wouldn't be able to pick up something that's porous because they need to be able to form a seal. So my student, Yusuf Golestani, decided to consider, well, what if we look at a matrix of defects and we can, you know, use what we've learned from structures of defects in liquid crystal, you know, regular liquid crystals, not necessarily polymers, to kind of spread the core of the defect out a little bit. And he tried some different parameters. And this is an actuation that came from a flat surface. When actuated, it forms these octopus sucker-like shapes. And if you look more closely, you can see how the finite element mesh looks. So the idea here is that these could be fabricated on the surface. Either it could just be on a solid surface like any coating, or it could actually be on a liquid crystal elastomer ribbon that could then actually be a biomimetic octopus arm. So the ribbon itself could have the capability of actuating and so on, but the surface treatment would allow it to suck onto a sample. So for instance, you know, ideally it could like pick up an iPhone. Oh, good grief. So, sorry, I didn't realize I had that phone on right now. So another thing we've been working on is another kind of coating where we have defects that are not little points on the surface, but are actually long lines of defects in the material. So if we have 2 pieces of glass, again, that are patterned, one of them has uniform planar anchoring. So the liquid crystals are lying parallel here, parallel to the y-axis. And then we have another kind of structure here we call C-stripes. So what's going on is the nematic director, as you go across the stripe, is just rotating. So theta is proportional to x, right? It's just going around and around and around. If you put one of these on top of one of these, some magic happens, and the liquid crystal in between forms an array of parallel, extended, identical disclinations. This is not a defect structure that can occur with dislocations in crystals. If you have equivalent defects, the energy explodes in crystalline solids. But in this soft matter material, with this anchoring, we can, in fact, and these are +1/2 defects, they can all be identical, and you get an evenly spaced array of extended disclinations. For experts in the audience like Chuck Rosenblatt, I will say that's because there is, you know, escape in the 3rd dimension, and we've actually done some work with Chuck to understand how the nature of disclinations in liquid crystals. They are fascinating things. But this way, so here, this is a little mock-up picture. So on one surface, you have this patterned thing. On the other side, you have this uniform thing. And in between magically forms this parallel array of defect lines. Okay, so if you take that, you build that thing, and then you take one surface, take the glass off, and then heat it up, it forms little microchannels. So this is an actuatable coating, a programmable actuatable coating. This is Greta Babahanova, who did this experimental work together with her colleagues from Oleg Lerventovich's group. And so the material, if you take a stylus and go across, the pattern goes up and down. So this material, these grooves get thicker as you change the temperature. So heating here from 25 degrees up to 100 degrees, you see these beautifully symmetric channels. But sometimes she saw channels that had a double well structure, and sometimes the channels were not symmetric. And those were questions like, why would that happen? Simulations can answer those questions. So the questions we might have, like, what design factors control how the channel forms? What would give rise to, you know, one kind of pattern, another kind of pattern that wasn't what we expected? So to model this, what we decided to do is we had to do 2 types of simulation. One, we have to figure out where the heck are the disclinations for whatever set of parameters, what you do with the anchoring surfaces, and what are the properties of the liquid crystal you put in between. And then once we know the director field, then we can put it into our finite element simulation. And from the point of view of the experiment, they had two options. They could take the glass off that was the pattern side, or they could take the glass off that was the uniform planar side. And they got different structures both ways. And they're like, why? Again, you see an experimental colleague and they're like, what does my experiment mean? Why is it doing this? And so the simulation tools can answer some of those questions. So a student working with me, Sajida Afka, who is now at Microsoft, she did numerical simulation. Now, we didn't know the Frank constants for their liquid crystal, so we just used the ones for a common liquid crystal 5Cb. She did the, so if the C-stripe side is on the top and the planar side is on the bottom, the disclination line is right in the middle coming out of the board, we could figure out what the director field is. And we just did that by minimizing the Frank free energy, which describes the energy of elastic deformation of a liquid crystal, using a simple finite difference method. So that's, not rocket science, but it's an important piece of the puzzle here. So not the main part of her dissertation, but she did that to help us out. And then the question is, okay, so Greta Babakhanova asks, when I put those two pieces together, what if I accidentally misaligned them? And it's like, well, we can do this simulation. And so we misaligned them by 15 degrees. And what we found was, then your channels become asymmetric. And so this is actually the channels turned upside down, so they look like shark fins. And so, there's a symmetric case and there's a symmetric case. So sure, if you misalign the two faces, that's one reason why they might be asymmetric. And then the other question is, what about the double well structure? Here my husband, Jonathan, came to the rescue. We had done some simulations, but he said, if the displacements are very small in this film, we could make some very simple assumptions about linear elasticity. He did analytical calculations, and what he discovered, which our simulations also showed, that if the disclination forms too close to one of the two surfaces, you get a double well. If it's in the middle, you get a single well. Pretty simple. You're trying to engineer something, it's good to know what's going on. And then it turns out, well, you would think the position of the disclination just depends on the liquid crystal. What are the Frank constants? What are the bounding surfaces? But the issue is when you're photopolymerizing it, the dynamics of photopolymerization might depend on how close the UV light is and how long it's, so you could end up with the disclination in different places. So even when they tried to repeat the experiment, sometimes it didn't come out exactly the same. And then of course we wanted to do the full 3D picture. So here is if the uniform side is free, what you get, and if the pattern side is free. And here's some things that we learned. Sure enough, if you just look at the middle, we see the same type of structures that they saw in the experiment. But if you look at the whole sample, there's a lot of relaxation happening because of elasticity at the edges. So there is a mechanical constraint that this very thin elastic film is attached to a substrate, and we don't allow it to debond in the simulation, nor does it debond in the experiment. But there are displacements. You get kind of a rippled edge that comes from displacements actually in the plane, not even just out of the plane. And so if I were in the lab and I fabricated one of these and I said, wow, the middle of my sample looks beautiful and perfect, but the edges are kind of a mess, I would trim it. I would cut it. And you know what? It would wrinkle up just the same. It's an elastic relaxation. It is not because something bad happened when you polymerized the material at the edge of the sample. It is fundamental to the elasticity. We also find that if the pattern side is free, we get a bigger deformation than if the uniform side is free. That agrees with the experiment. We were also able to use the simulation to estimate some of the underlying material behavior, the parameters that describe the material behavior. So the simulation helped understand the experiment. This work has been submitted to the Journal of Applied Physics and it's in revision. So we have high hopes that they might accept it. I'm going to skip those other topics. I have like 1 second left. The finite element code can be used for a lot of things. One thing, it can be used in 2D. It can be used to model deformable colloids. So I started a collaboration with Craig Maloney, and I was helping to mentor then an assistant professor, now I believe an associate professor at Slippery Rock, Manuel Valera, who's an old friend of one of my grad students. And we could see, when you squish polymers, squish colloids together, they can make these beautiful polygonal structures and they can have these structural transformations that arise as the sample deforms. So this would be a great model for modeling deformable granular materials, including what happens when you sit on your beanbag chair. And they don't even have to be disks or spheres. They could also be triangles, and then we could do squishy triangles. I mean, why not? And of course, this could be 3D instead of 2D. So once you have your own finite element code, there's a lot of stuff you can do. We are also interested in active matter. This is a system I've been playing with for a long time, although I'm sorry to say we haven't published anything much about it. We call this problem snakes on a plane. And in particular, my student Michael Varga has been working on modeling a phase diagram. So here we have, let me say, on the two axes, we have, well, anyway, one of them is density and one of them is bending modulus. So it's getting denser to the right, and I guess it's getting stiffer going up. And you can see, this is sort of a moving phase diagram, very different types of behavior as a function of, so you have far more interesting active matter behavior on this corner than on this corner. Let's see, I need to get this thing to stop. We can also put those things on non-flat structures and observe how topological defects respond to curvature. But I think I will skip that. And just mention here are some of my collaborators. As I mentioned, Mike Varga is local to the Cleveland area and might be here on the call today. Yusuf Golestani will be finishing his PhD soon and will be looking for a postdoc or an industry position. I mentioned Biane is teaching at Lincoln University in Missouri. Andrew Konya started a company called Remesh, which is an AI-based company, has nothing to do with meshing finite element simulations, but maybe that's where he got the idea to use the word mesh. He's gotten, I don't know, tens of millions of dollars of venture capital, and his company is a going concern now. And he actually hired Michael Varga. So I can't get either of them to work full time on modeling liquid crystal elastomers at the moment, but at least Michael's still making progress towards his PhD. My husband, Jonathan, many of you also know, and this is Dick Brower and his former student, Anne Helen Jelabar, who is, I believe, postdocing also at Eindhoven right now. So I'll just put up my conclusion slide. The most important thing is to say what we're doing next. And the answer is what we're doing next is we're trying to use machine learning to solve the inverse problem. Everything I told you about so far was the forward problem. Like, you tell me the nematic director field and I'll tell you how it changes shape. The machine learning issue is the inverse problem. You tell me the shape you want and I'll figure out how to design it to get that shape. So that's what we're doing. Thanks very much for your attention. It's kind of weird lecturing when you can't see the community that you're with, but I'm happy to answer your questions.
Well, thank you very much, Robin. That was a very, very interesting talk. I think the artificial octopus that you invented is really a candidate for the Ig Nobel Prize at some stage.
I like that idea. So I think Oleg has, one of his students is actually fabricating it. Everything got kind of postponed when the pandemic caused us to close our labs, but labs have been open for a while. So I hope we'll have, hopefully, besides being a candidate for the Ig Nobel Prize, it would actually be useful for something. It would be, I don't know, what could you pick up with an octopus suction cup that you can't pick up with, say, a robot claw?
Interesting. I'm sure the Office of Naval Research might have some defensive applications for that. But I should open this up to questions from the audience. I think using the chat function, is that how we work it, Harsh, now?
Well, the other thing is, yes. I can do stop share, and then I can see everybody. Unless you really want to stare at my conclusion slide.
No, that's
okay, and that means I can see what's in the chat, which is nothing at the moment.
Right.
Okay, Robin, I'm going to avoid the chat.
Okay.
Just go ahead and ask a question or two, depending upon whether anybody else wants to come in. I know experimentally this would be one hell of a problem. I don't know if you thought about this theoretically, but some of these patterns, what might happen if you start dealing with biaxial nematic phases?
Then they would have an anisotropic transverse response. So while it's shrinking along the nematic, the growth in the other two directions might be different. And then we would have a more complex actuation because it has not only one, but two special directions.
Yeah, I suspect that's something that's going to happen experimentally in the near future, but I don't know if that's something that would interest you in terms of actual calculations.
Well, then here's my challenge for the experimenters. We know how anchoring aligns the director. How do you align the other axis? If I can't control it, I can't design it.
External field, maybe.
But you need to both, okay, so you can use anchoring for the director and the external field for the biaxial direction. Will that work?
It's been done. The thing is, it's been done in bulk systems, not on sort of a pixel by pixel basis?
Well, from the point of view of making an artificial muscle, having a muscle whose contraction in one direction induces different strains in the other two directions, there might be a use for that, but I don't know what it would be. From the point of view of patterning it, again, it's one more control parameter from the point of view of design.
Okay.
So one way to think about it is if you just put a director field, that's uniform through the thickness of the body, then you can get one, degree of actuation. If you have a twist through that or a splay through that, that's another degree of actuation or another degree of control. If you have a 3D vector field that exists in a whole block of material that you made by 3D printing or the layer by layer deposition, and you can really control what happens in each voxel. I mean, Tim White and Jennifer Lewis have made some really strong artificial actuators that can do, instead of the first papers, they always seem to be lifting paper clips. Okay, and then they started lifting like actual weights. Like they can build these materials with muscle, that can really do significant amount of work. Also, Taylor Ware has been working on biomedical devices made of these things. He's, working with doctors trying to come up with applications. But yeah, the biaxiality I hadn't really thought about.
I have another question, but I'll let someone else go first if someone else has a question.
There is something in the chat, but nothing, it just says if you have questions, raise your hand.
Okay, let me jump in with one then. In your molecular dynamics days, you were conserving energy rather loosely, and so there were thermostats involved that ensured that the temperature remained the same. How does that work with a finite element analysis that you control temperature?
It's not a molecular simulation, and so the same types of statistical mechanics are not expected. However, we have internal dissipation, so the lossy part of the thermostat, the drag forces, are present. And then if we want to have a little bit of noise, we add a Langevin. We can still use a Langevin noise. I'm trying to think, why would we do that? If the system is, actually, I can, in the finite element simulation, I don't think we've ever added the noise, but we do add dissipation. So the driving force for actuation comes from the change of temperature or the light or the electric field. And that makes the material want to move. And if we didn't have any dissipation, it would oscillate forever. But the adding dissipation allows the material to either in an underdamped way or an overdamped way come to mechanical equilibrium. So we don't normally need a thermostat for the finite element simulation. I suppose if we were trying to model at the molecular scale, we would have to add that. There have been some simulations. Claudio Zanoni and coworkers have been doing some molecular simulations of finite element. Of liquid crystal elastomers, not finite element, real molecular simulations. And Viana Jimenez Pinto is thinking about pursuing that further, could answer questions about the molecular design. There's so many different types of materials that have been studied. I'm not much of a chemist, so I can't tell you the great advantages of one or the other. But yeah, I don't think that finite element simulations in general need a thermostat, because you're describing the mechanical evolution of a lab scale object. Thermal fluctuations don't make it move very much.
Okay, thank you. So I'm not seeing any other.
I had a question.
Like Jack gets to go again.
Okay. Actually, can I go first? I did have a question. It turns out as a host, I can't raise my hand. So, so I just have to barge in. But I guess the question was just about, those were beautiful simulations and it was really fun to watch them. I wanted to back up to the very first one where you didn't even have any liquid crystal. It was just pure elasticity. And you mentioned that it was nonlinear. So I was wondering how essential the nonlinearity was.
The nonlinear aspect of it is the strain. So the first inspiration I had for this work was a multi-scale simulation by Tim Kaxiris from Harvard. He was, and his coworkers, They were studying crack propagation in silicon, and they decided to use a tight binding model for what happens to the little chemical bonds at the tip of the crack that are actually breaking. And they did molecular dynamics in some fracture process zone around that where dislocations were being generated and moving. And then in the far field, they did finite element. And I looked at their finite element algorithm and said, I could implement that. And they just had a term that went like epsilon ij, epsilon KL. And if you define epsilon, the strain, so you have this displacement function U, which is the X displacement, and V, which is the Y displacement, and you can have a third one, W, which is the Z displacement. DUI dxj plus DUJ dxi is the linear strain. And I wrote down that strain energy, epsilon ij, epsilon KL, and then I realized if you rotate the sample, the energy goes up. And that can't be good physics. Like when you change where you draw your axes, it can't change the energy. So you get fictitious torque. Mm-hmm. So instead we use this other form called the green Lagrange strain, which has, again, I learned it from reading Landau and Lifshitz, which, I guess a lot of mechanical engineers maybe don't read, but they read books on solid mechanics that have the same material. It has a second term that goes like, let's see, DUI dxj, DUK dxi, DUK dxj. So it just has a nonlinear term in the strain. And then when I write the energy as epsilon ij, epsilon KL with that prefactor with those Cij KLs, then energy is conserved when you rotate the sample. So a mechanical engineer who's trying to decide if the bridge is going to fall down off the river on a hot day, the strains are so tiny, a fraction of a percent. And there's not much rotation. So the linear approximation is just fine. But, I was looking at the experiments by Peter Palfi-Mahori and others who were like, the object is rotating 60 degrees. It's not a tiny displacement. So the linear approximation is terrible. We can't do that. On the other hand, Jonathan used linear elasticity to model the deformation of a very thin elastic film on a rigid elastic substrate. A rigid not moving substrate. And the displacements are tiny and the linear approximation is fine. But he wasn't able to do that for like the whole sample with the edge effects. He was just doing essentially, he could solve it analytically for a very simple, more or less two-dimensional case. And the finite element lets us do the full 3D problem. So, that's what makes this problem so transdisciplinary. It has the mechanical engineering of like elasticity of solids, which we don't usually think of as physics. We think of that as, solid mechanics. And then it's got photochemistry and chemical synthesis and processing. And then photo patterning. So it's a pretty rich multidisciplinary thing. I don't know all the pieces of it myself. I've never run a 3D printer. Luckily, I have colleagues who do. And there's some other fun things. So Chuck has been working on how you pattern surfaces to create defect lines that are not just, again, points or long lines, but actually have shapes like an arch. So now we have ways of patterning liquid crystals with all kinds of interesting microstructure. This is materials by design. Like we can put all kinds of interesting structures in. We just don't know if they'll produce anything interesting in terms of liquid crystal elastomer actuation. But Chiho, for instance, has figured out how to make a triangle-shaped disclination loop that floats between two substrates, and not just one, but a whole array of them. So imagine if you could blow smoke rings in the shape of triangles. Okay, I don't smoke, so I've never tried to blow a smoke ring. But anyway, it's a rich system with unique pattern formation capabilities. So anyway, the nonlinear elasticity was a surprise for me. Like I said, when I wrote the code the first time, wait, why is there fictitious torque? And I read the solid mechanics part and I laughed so hard I fell off my chair. It's like, what? How can you write that as an energy when it's not invariant under rotation? That's a terrible energy.
Okay, so Chuck still has his question.
I'll let the question go in the interest.
With his permission, we'll move to an informal mode to hear Chuck's question.
Wait, there's a question from Annette.
Recording now and formally terminate the proceedings, but proceed then with informal discussion. And Chuck gets the first word.
Okay, I was going to say there's also a question from Annette.
Glenn, before you go, we'll meet after this is over. Okay, maybe about 10 minutes.
So there was a, oh, I haven't been looking at that. Right, yes. So Annette, would you like to, can you unmute yourself or do I have to do that?
No, she can unmute herself. Yeah. Everyone can unmute themselves if they want now.
So I was just curious, I was thinking of applications that you would want something to move without people being around it. And one of the things I was thinking about was with something dangerous like a radiation or a dangerous chemical. Can you have these things respond to like high energy radiation or a dangerous chemical?
I have not seen them. I have not seen them respond to radiation. I don't think anybody's tried that, but they certainly respond to chemical environment. And again, if there's, for instance, solvent in the air, and Peter Palfi-Mahore has worked extensively on that, when the material absorbs solvent, the degree of nematic order drops. And that can cause actual, I mean, first of all, it will swell from absorbing solvent, but it will also actuate. And in this case, I guess it would, yeah, it's the nematic order is getting smaller. It will shrink along the nematic director. And so you could have a lid that will open as a function of temperature. Hang on, Annette, I need to pin your video. Now I can see you. So, do you have a specific application in mind?
Yes, I was thinking about a seal, like a fail-safe seal. Like if you had something that was dangerous and your seal fails, if you could have something that would then respond to it and double over, then first of all, you could just have like a video or something, see if one of the seals has doubled over. Second of all, you could get it to seal, hopefully again, to protect people.
Interesting. Well, and there's various options here. So one is to make a material that just responds to the chemical environment. And the other one is to have a material that responds from, for instance, shining light on it or applying an electric or magnetic field or any other stimulus that makes the material change shape. I guess from my point of view, you would really also just think about sensors in general. You know, that you're going to have a material that's going to change color or change shape in response to a change in chemical environment. And I know there are people working on that kind of application. You know, as far as biomedical applications, I suppose you could also think about if you had minute particles, you know, drug delivery, because you have things that open. Let's see, there was, what was his name? There was a biomedical engineer at Johns Hopkins, whose name is escaping me this second, who had materials that he was using in like to biopsy what's happening inside the digestive tract. So you would have like little actuators that are like, they have their mouth open when you put them in, and then they change shape in response to the local environment, whether it's temperature or chemicals, and they snap shut and they grab small amounts of material, and then you suck them out again, and then you open them and you retrieve the material. So those are like, as an alternative to having like a mechanical biter that grabs tissue on the edge of the intestine to take really micro samples. Okay, this is getting on my nerves. So it's a.
Well, before we get too deep into the intestines, maybe now it's time to stop the formal proceedings and continue informally. So let's thank Robin for this delightful talk.
Thank
Thank you.
Okay, so if you had more to say on that, or if we switch to chat.